listed here. There's a couple of reactions that we're not actually going to go through, and I put them here just for your reference. A lot of times they're omitted from the classes. One here, even though it says a great name of three people, is Hell-Vollard-Zelinsky reaction. A lot of times it's omitted, but I put it here as a summary if you want to. But it's a way of actually introducing a halogen alpha to a carboxylic acid, as opposed to an aldehyde or a ketone. So I put that there if you want to look at it for fun. And there's a couple more towards the end for that. But what we would like to look at now is, let's consider, rather than acidic conditions, let's go to basic conditions. So now notice we have a ketone, and we react this with bromine, now with sodium hydroxide as our base. And it looks like we actually brominate, and we end up with two bromines on here. Now I put two methyl groups on the left side just so that we don't have to worry about adding to either side. We're only considering the one side. So now why is it that with the two bromines, we actually under basic conditions, we end up with two bromines? So let's think about a mechanism for that. So these are just a roadblock over there. So we have the hydrogen, we have two hydrogens. Let's just consider one. And under basic conditions now, let's go ahead and deprotonate. And we'll just write the resonance structure with the electrons on the carbon. So we've generated now our enolate ion, which is going to be a good nucleophile. Now we don't have to worry about the proton transfers like we had under acidic conditions, but we can just go ahead and have this enolate attack Br2 and brominate. And I'm going to ignore stereochemistry. Put the other hydrogen in here. So this is a chiral center, but we're going to take care of that in a minute. Now, the thing to notice here is that, going back to the far left, we said this proton that's stuck here between all these arrows was acidic because of the resonance stabilization with the carbonyl group. So that's why we can take the proton off. It's alpha to the carbonyl. We could draw the other resonance structure here for our enolate ion. Now, if we were to take this proton off here, we could actually do the same thing. We could draw a resonance structure, it's just for formation of an enolate. But this proton is actually even more acidic than what we started with, because we have this electron withdrawing bromine, which we didn't have before. So if our base, hydroxide, is able to take off this first proton, it's even more energetically favorable to take off the second proton, because now we have this electron withdrawing bromine. So we can't stop the reaction. We're going to deprotonate again, generate our enolate. I'll write it as an equilibrium. All this stuff is the same. Another enolate, and then this one will react with bromine. So this can explain why we end up with two bromines. Okay? So the basic reaction is a little bit simpler compared to the acidic conditions. We're taking our proton off, generating our enolate, which is resonance stabilized. That's acting as a nucleophile with Br2 to brominate here, the alpha position. And the remaining proton is even more acidic because of induction with the bromine there. So we've been seeing induction increasing acidity. So now the base can take off another proton, and then this will generate the enolate again, which reacts with bromine and generates the dibromo compound. And then you're done because you don't have any more protons. Now, if you didn't have these methyl groups here, you could actually end up having 4 bromines attached to this. So before we pause for just a couple of minutes, let's take a look at one more reaction, which is going to be a little exhaustive to write out, but it's going to be the same idea that we saw here with one twist. And this is known as the haliform reaction. This is an important reaction. We can take a compound that's a methyl ketone, So it's a ketone here. What's really important is that this is a methyl group. And if you have a methyl ketone and you react it with 3 equivalents of some halogen, that's what X2 is representing here. So chlorine, bromine, or iodine. And in the excess of base, the strange thing is you actually end up with a carboxylic acid. And then you generate what's known as a haloform. So the most commonly known haloform is CHCl3, which is chloroform. Or you could have, if it's bromine, it's bromoform, or iodine, it's iodoform. This is a classic way in the earlier days of identifying if you had a methyl ketone. You would carry out this haloform reaction with iodine because it would generate a yellow solid in the reaction. So let's go through and think about how we actually get to this carboxylic acid. And everything actually follows what we've already seen, except there's one twist. So we have 3 protons here. And then in the presence of hydroxide, let's go ahead and take a proton off and form our enolate. So negative charge here. And I won't write the water that we formed. Now we formed our enolate. We could write resonance structures of that to show the stabilization. But this can react now with iodine. Kick out iodine. We'll put the I there, and we have 2 hydrogens. And you'll see the pattern here. So now, just like what we saw with bromine, introducing a halogen actually made the remaining proton above more acidic. Same thing here. So now we still have 2 protons, alpha to this carbonyl group, if we generated an enolate. And now we have this I next to this iodine, which is electron withdrawing. So these 2 remaining protons are even more acidic. So let's remove one. Doesn't matter which one. Let's generate our enolate. So we have the iodine there, like an H on the side. I'll just have the other hydrogen disappear for this. Let's have this react with iodine again. Carbonyl group, 2 iodines. Hydrogen remains. Now, as you might imagine, if one iodine up here on the right was electron withdrawing by induction, making these 2 remaining protons more acidic. Now we have 2 iodines, still have 1 proton. This proton now is even more acidic. So let's have another equivalent to the base. We're almost done with this one. Let's take this proton off. We're going to run out of protons. Let's see, let's put this one over here, this iodine here. Here's our enolate. We'll write it here to the left. 3 iodines. So now we have 3 iodines here. We no longer have any alpha protons that we can remove, but now actually something that happens, because we need to get to this carboxylic acid up here on the top. This carbonyl carbon now is going to become even much more reactive than a regular, maybe ketone, for example, because we have all of this inductive effect over here, withdrawing electron density away, these 3 iodo groups. We have a lot of extra base around, sodium hydroxide is in excess. So now what can actually happen, I'll scroll up again, is the hydroxide can attack in kind of our older type of reaction that we've seen. Tetrahedral intermediate. OH that we have here. And now this is where it's a slightly different step, is that all along we've been talking about with aldehydes and ketones, you do not have a good leaving group on them because it's a carbon or a hydrogen. However, it is possible that if you introduce enough electron withdrawing groups over here, for example, or you have enough of an inductive effect, you could actually make this carbon, a okay leaving group or a decent leaving group. So this carbon has all of these iodines withdrawing electron density away from it. So if we were to put a negative charge on this carbon, it could be potentially stabilized by induction. And that could explain how we end up with this carboxylic acid. So let's reform our carbonyl group and actually break the carbon-carbon bond. I know that goes against some of the things that we were seeing before, but if we have enough electron withdrawing groups on there, this can actually happen. Now we have ended up with a carboxylic acid, and then we'd have our iodoform precursor, which I'll just write down as Ci3. I'm drawing the carbon so it's a little easier to see. And now we'll quickly have an acid-base reaction. So this is just going to pull this proton off. Which now generates a carboxylic acid, plus, we'll write this in the more conventional way, CHI3. So the CHI3 is iodoform. What's useful about this is if you carry out this reaction, is that this iodoform generally forms a yellow precipitate, so a nice bright yellow precipitate. So this was a classic way, as I mentioned, of identifying a methyl ketone. So you find a compound, say someone didn't label it, unfortunately, but you suspect it has a methyl ketone in it. So what you would do is you'd react it with iodine, and an excess of iodine, at least 3 equivalents in an excess of base. And if a yellow precipitate crashed out of the solution, that's pretty good evidence that you have a methyl ketone. Oh, sorry, O minus. Yep, you're right. Okay, so this is one of those cases where this is a pretty long reaction. You're looking at all these different reaction steps, but it's the same thing over and over. And then hopefully conceptually, it makes sense in that we'll keep on making these remaining protons more and more acidic. So it's a lot of information, as mentioned before. We are going through things quickly. Why don't we pause for 6 minutes? If that's okay with others. I'd like to